Good morning. Welcome to lecture number 16. We're going to start the fun part, introduction of high performance concrete. Okay. In previous lecture, we have talked basically all the important information about concrete materials. Okay. What is cement? What is hydration of cement? What is shrinkage, creep? And we also discussed some durability issues. Okay. So from today, we're going to start talking about different type of high performance concrete. For example, here shows a cement car. Okay, this is cement-based materials. Okay, cement cross-linked with 5% of polymer. Okay, the tensile strength of this concrete, as we can see, is very, very high. Okay, 30,000 psi. Okay. Much higher than traditional concrete. As a result, we can make cement car and the cross-section of the material is very thin because the tensile strength is so high. Okay. This material is called micro defect-free or MDF cement. Use pressure to remove large voids and entrap the air. Okay. But the cost of this material is also very high. Research history of high-performance concrete. Okay, at early stage, the focus is on how to achieve the highest strength, okay, or high toughness. But later on, people realize high strength is not always equal to high durability or other type of performance. Okay, so then the focus will be on other type of performance such as durability. Okay, and later on, some other properties will also be focused, such as high flowability, such as self-consolidating concrete, or geopolymer concrete, which is sustainable concrete, does not need any type of cement. Okay. So high performance depending on what type of performance we want to achieve, not only limited to high strength. But today, high-strength concrete still has its use, especially for high-rise building. Okay, in high-rise building, because most of the concrete is inside, isolated from outside environment, so durability is not a big concern. And with higher strength, we can reduce the cross section of beam and columns, so we can reduce the dead weight. And also we can reduce the total weight of the materials. So the cost will also be lower. So high strength concrete right now is still being used in some cases. In early lectures, we discussed high strength concrete is not equal to high durability. Okay, one of the reasons is autogeneous shrinkage. So which is only occurs with low water cement ratio concrete. Because for high strength concrete, we use low water cement ratio concrete, and also very often we use silicon film. So that will reduce the pore size. Okay. And from the lecture of dry shrinkage, we know when we reduce the pore size, the shrinkage stress will be higher due to Kelvin-Laplace equation. And also for high-strength concrete, the water amount is limited due to self-desiccation or drying internally due to hydration. Because of these two reasons, high-strength concrete tend to have very high autogeneous shrinkage, and if they crack, the durability will be lower. And here shows an example of another high performance, high flowability. I think we mentioned this before. This is self-consolidating concrete. This concrete does not need any type of compaction. It can flow on its own weight and fill every corner of the formwork and also go around reinforcement. Okay. As a result, we can pump this concrete over very long distance. Okay. The pumping speed is also very high, up to 200 cubic yard per hour. Okay. Remember in 2011, there's a earthquake and tsunami in Japan. Okay. One of the nuclear reactor is called Fukushima reactor, has some leakage, and people thinking of using SCC to entomb everything, okay, just in case nuclear reactor is out of control. But luckily, we do not need that. Okay. And I will show you a video of SCC. Okay. We'll do another share. All right, so this is a video of SCC flowing. We can use pump and flow under its own weight and feel every corner of the formwork. Even though the rebar is very dense, you can still go around the rebar and achieve very good bonding. Right. So to achieve the design performance, either is high durability or high strength. Okay. The fundamental approach is based on what type of performance we want to achieve. Okay. We need to focus on properties of raw materials, what type of raw materials we use, okay, including admixtures. For example, flash, silica film, chemical admixtures such as superplasticizer. Sometimes special processing technology, such as using high pressure or heat, or even extrusion, can also be used. Okay, and we should also focus on nano and microstructure of the materials. Okay, we can use chemical analysis or XRD, which is X-ray diffraction, scanning electron microscope to study the chemical reaction as well as microstructure of the matrix. All right, so this table summarizes the property of conventional concrete, high strength concrete, and ultra high strength concrete. You can see for normal concrete, the strength typically is lower than 50 megapascal or 7 KSI. For high strength concrete, it is higher than around 100 megapascal. Okay, 1 megapascal is equal to 7 KSI. Okay? For ultra high strength concrete, the strength can be higher than 200 megapascal. For the water cement ratio, we can see high strength concrete is around 0.3 plus minus. For ultra high strength concrete is even lower than 0.2. Okay. So without chemical admixtures such as superplasticizer, it is almost impossible to achieve such a low water cement ratio. Okay, so high range water reducing admixtures are necessary for high strength concrete and ultra high strength concrete. Okay. For mineral admixtures, it is not necessary for conventional concrete, but it is important or even essential for high strength and ultra high strength concrete, especially for silica film. Okay, silica film can greatly improve the pore structure and refine the ITZ, which is bonding between the paste and the algae. So for all the high strength concrete, we should use at least 5% of silica film. Okay. Sometimes fibers are also used to control the cracking of high-strength concrete. Okay. For processing techniques, okay, for high-strength concrete, we can use conventional processing mixing procedure. But for ultra-high-strength concrete, heat treatment and pressure are necessary. And you can see from here, this is chloride diffusion rate. The lower the diffusion rate, the better durability. Okay, and you can see ultra high strength concrete has much lower diffusion rate compared to conventional concrete. But keep in mind, if the concrete crack, everything will be off. Okay, so make sure the concrete will not crack. Okay, if the concrete crack, even though the chloride diffusion rate before cracking is maybe very low, but after cracking, the durability will be bad. And here shows stress and strain curve for conventional concrete and ultra high stress concrete. Okay. For conventional concrete, it has classic strain softening or quasi-brittle behavior, which means after the peak load here, the concrete can still resist some of the load. Okay. Ultra high strength concrete has much higher strength, and also the slope is much steeper, which means modulus of elasticity for high strength concrete is higher. And there's not much post-peak behavior for this high strength concrete. As we can see, it is pretty brittle compared to conventional concrete. Not too much post-peak behavior. Okay. But if we can add some fibers in this system, we can make it tougher. Okay. The reason for these brittle materials of high strength concrete is because this is for conventional concrete. We have the so-called crack localization, which means cracks in certain location will opens up, and that causes the failure of the concrete. But in other part of the concrete, it still remain untouched mostly. Okay, and that's the reason we have this post-peak behavior. But for high strength concrete, because we improved ITZ, improve the breakage link so much that there's basically no weak link in high strength concrete. So the crack pattern for high strength concrete is similar to mortar or even cement paste. Okay. So as we can see, for conventional concrete, it try to go around ITC. Okay. So we see the crack pattern like this. But for mortar and paste or high strength concrete, the crack pattern is more strict. All right, so next, let's look at a couple of examples of high performance concrete. This is example, so-called ultra high strength concrete. Not only has higher strength, but also very durable. This is a project I participated in San Francisco Bay Area before I joined UH in 2011. Okay, so the goal is to design ultra high strength concrete. We also use fibers to make it tougher and more durable. Okay, it should be strong enough to resist an impact of high-speed heavyweight truck. Okay, we do some impact tests, which I will show you in a moment. And because the concrete will be put near the pier, close to the seawater, it should also be very durable to resist harsh marine environment. Okay. So to achieve these goals, we base on particle packing series, not only for aggregate. Okay, we use very strong aggregate such as silica sand and quartz powders, but also focus on packing density of powders such as cement and silica fuel. Okay, we try to achieve very dense system to improve the strength. We also focus on achieve desirable rheology using high-range water reducer, high-end water reducer such as superplasizer, and also use fibers to enhance the toughness of concrete. Okay. We also focus on cement chemistry and microstructure analysis to ensure we have a desirable hydration product and microstructure. Okay. Here shows packing models we use trying to achieve the highest possible packing density for the system. Right. So the end result is ultra high strength fiber reinforced concrete, the UHSFRC. Strength is higher than 200 megapascal, around 30 KSI. The fracture strength is also very high. Okay. Very, very low chloride iron diffusion rate. Okay. We use this concrete to make a so-called street furniture like this. Okay. People can sit on this as a bench. Also, we can use it as a planter to decorate. Okay, but actually, it's the anti-terrorist barrier. Okay, to protect a certain critical structure in the San Francisco Bay Area. Okay, so the barrier should stop 15 kips truck, which is similar to Ford F-750. Traveling at 50 miles per hour within 3 feet. Okay, I'm going to show you some of the video. Okay, I'm going to show you my iPad. Okay, so here is the real impact. Okay, this is F-750 traveling at 50 miles per hour. That is prototype barrier. The test is done in the desert area in Los Angeles area. Okay, so near the Ontario airport. Okay. We did this test, as remember, in 2008. Okay. And we have another video. This is a slow motion of the impact. The truck. That's the barrier. Okay, we have some anchors underneath the barrier because the barrier will be anchored to some pier, which is not very thick. The concrete is not very thick. So we need to use some pistol anchors to reduce the impact load. Okay, this is the slow motion of the impact. All right. So this is the Department of Defense project. Some more pictures. This is the aftermath, okay, of the truck. This is ESTM standard test. Truck traveling at 50 miles per hour and is stopped by the barrier within 3 feet, less than 1 meter. So here is the impact surface. The concrete actually is very good. Okay, just some dirty engine oil from the truck. Okay. Actually, we did another impact on the same barrier. Okay, one is the impact in the middle part, in the middle section of the barrier. Another is impact on the side. Okay, so this is one of the fun project. I'm going to show you another project which is currently performed at UH Manila. Okay, this is called geopolymer concrete. Okay, here. Also, this is a video from 2015. We cast the prototype geopolymer concrete in Big Island. This is the news about it. Okay. This is my former students, Ahmed and Ian. This is geopolymer concrete, and the rebar is not traditional steel reinforcing rebar. It's made by asphalt. Asphalt is type of mineral which will not corrode.
So this project is a joint project between Pisces and the County of Hawaii to put a sidewalk in here in Hilo, but not an ordinary sidewalk of concrete, but a sidewalk made of basalt, the same basalt that makes up the Hawaiian Islands. The reason that we're interested in this is that Pisces does technology development work on how we can do construction on Moon and Mars. When we go settle Moon and Mars, we can't take construction material to us with us from the Earth. We have to live off the land, if you will, by using the resources that are there on Moon and Mars. And what we found is that the basalt material on Moon and Mars are exactly like it is on the Hawaiian Islands. And so what we're doing is developing some technologies by testing it here in Hilo of construction using basalt material instead of concrete that we can apply to Moon and Mars. At the same time, we're looking at how we can do similar civil engineering construction here in Hawaii using native material, indigenous material, rather than having to import many thousand tons of concrete from the mainland into the state. If we're able to do that, it would save significant cost in using basalt material instead of concrete for civil engineering projects. This project is very unique because it blends 5 different groups together. The County of Hawaii, the County Research and Development, the state level, which is Pisces, the federal government, which is NASA, the space agency, academia. One of the pads we're putting in is done by the University of Hawaii at Manoa Civil Engineering Department. And then the 5th group is the private sector. One of the pads we're laying down uses, instead of steel and iron rebar, it uses basalt rebar. And that comes to us from Kodiak Rebar in Houston, Texas. So we're very excited about that. And it blends then into this one sidewalk, 5 different groups that are working strategically together to do something very unique, something very different for the state. One of the goals for Pisces is what we call dual-use technology. Not only technology that we can use on Moon and Mars, but technology we can also translate for use in terrestrial applications for the benefit of the state. And this is one of those applications of showing construction technologies that can be used on Moon and Mars, but also that have application within civil engineering projects within the state of Hawaii, within the Isles. Sidewalks, streets, patios, piers, berms, foundations, all that might be able to be made out of basalt material instead of concrete.
So there's a need to figure out how do you...
So over the next year, we're going to be evaluating different options for assessing the pads here on the sidewalk. Compressibility test, tensile strength. We're going to be taking cores out that University of Hawaii Manoa will evaluate, and then see how these pads perform over the course of a year. So perhaps a year or 2 from now, we could move into other civil engineering projects within Hilo, Big Island, across the Isles, out of basalt instead of concrete.
Everyone ready?
Okay. So he mentioned basalt materials. Actually, we use flash, okay, and some slag. Okay. In this concrete, we do not use any Portland cement, so we can reduce the cost associated with Portland cement. And also we reduce greenhouse gas production because during the manufacturing process of cement, it generates a lot of CO2 and other gases. Okay, so we use waste materials such as coal ash, fly ash, slag coming from steel manufacturing, sometimes red mark, which is a waste from aluminum production. Okay, so we use these waste materials to place Portland cement. We reduce the cost, we make the environment better, preserve the environment, and also we achieve high performance. Okay. All right, so this is another project we have here at UH. The last part, let's talk about the basic design principles for high performance concrete. Okay, so first of all, the workability should be good enough. Okay, based on mixed proportions, we can change, for example, water cement ratio. We can change size and gradation of aggregate. We can use mineral mixtures. Okay, sometimes chemical mixtures to achieve desirable workability. Okay. The set time should also be acceptable. Okay, it is controlled by cement type and source. Okay, for example, type 3 cement, we have higher early strength, short setting time. Also controlled by the fineness of cement, and of course, chemical mixtures such as accelerator and retarders. Okay, that can control the setting time of concrete. And also acceptable rate of strength gain, depending on your requirement. We can control that from type of cement, temperature control, if we can do that, and also admixtures, such as accelerator and retarders. Okay. In lecture number 10, we talk about ACI mixed design method, okay, from ACI Committee 211. Okay, so unfortunately, this design method has some limitation. For example, it assumes water cement ratio and air content are only issues that affect stress. Okay, actually, mineral admixtures, even chemical admixtures will also affect the stress together with water cement ratio and air content. It also assumes MSA, which is the maximum size of algae, and water content as well as air content are only issues affect slab. And we know, for example, superplasticizer can easily control a slump of concrete. So that does not considered by ACI 211. And it's not very accurate for low water cement ratio concrete and does not account for superplasticizer dosage. And also does not account for mineral admixtures at all. Okay. And it does not allow slump to be adjusted by superplasticizer. Okay, so that's some limitation in the ACI 211 method. And here's some more recent mixed design method. I believe there's more versions. This is also from ACI Committee 211. The report is for high strength with Portland cement and fly ash. Okay, another ACI report is from another committee, 363. Again, I believe we have a newer version. 92 means version in year 1992. Okay, you can check for a newer version for this report, which is state of art on high performance concrete. And here are some minor issues about, for example, what age we test the strength. Okay, typically we test the strength at 7, 14, 21, and 28 days is the last. Okay, but we can do some other days. For example, if we use flash in the system, we may check the strength at 56 days, okay, which is 2 months, because the reaction of concrete with flash will be slower because post-dynamic reaction is slower, right? Okay. For the strength sample, normally we use 6-inch by 12-inch. So 6-inch diameter, the height of the cylinder is 12-inch, but we can use smaller cylinder. Okay, that could be we did in our lab. We use 4 by 8-inch cylinder, okay, to save some materials for other dates. Right. And this is some of the high performance concrete resources, for example, books, report, and also a website we can use. Okay. All right. So the key idea for this class, remember, high performance is not equal to high strength. We can define many different types of performance, such as flowability, sustainability. Okay, if we want to make the concrete greener, or high durability. All right. The last lab for this class is high strength concrete design. Typically, when we have real labs, that the students design the concrete and cast the concrete based on their design, and we're gonna check the strength. The group with the highest strength will have some words in the final grades. Okay, but because in this semester we only do the demo, so we cannot do the real casting. Okay, but let's submit your group high strength concrete mix design. Okay, the due date is November 18th. Okay, and please provide reasons for your selection of materials. Why you use this type of materials? Why you use, for example, 3/8 inch of coarse aggregate instead of 3/4 inch of coarse, and why you choose a certain parameters such as water cement ratio, or certain type of admixtures, or even the curing compound. Okay, what temperature you want to cure the concrete and why. Okay, it is not necessary to provide these detailed mix design steps. Okay. The materials you can use for your high strength concrete design, including type 1 cement. We only have type 1 cement in the lab. We have flash, silica film. Okay. We have superpositor. We have VMA. Okay. You can provide your desirable chemical admixtures or even mineral admixtures, but just state why the reason you want to use these materials. Okay. For the aggregate, we have two sizes, 3/4 inch and 3/8 inch. This is for coarse aggregate. We have basalt sand and also Moai dune sand. Okay. We have compaction table, we have curing gas, we can control the temperature to cure the concrete. Okay, we have still no materials in the lab, but if you want to provide some fibers, that's fine. But you cannot use rebars in the concrete. Okay. You can specify what temperature you cure the concrete. So in the other curing compound, you want to cure your high strength concrete. And tell me what. Okay, some suggestions and limitations. Try to use higher cement amount. Okay, that is because use higher cement amount, you can achieve a lower water to cement ratio. Okay, which is important for high strength concrete. Okay, you should use some silica fuel, at least 5%, but no more than 20%, I would say. Okay, so superpositor is also very useful to achieve the desirable workability. Okay. Okay. Usually you increase amount of coarse aggregate and reduce amount of sand compared to normal concrete, because the more sand you put in the concrete, the workability will be lower. Okay. And think about what size of coarse aggregate you want to use. You can go back to previous lecture about how the size of coarse aggregate affect the strength of concrete. Okay, and do some literature research, at least my handout on high strength concrete design, which I will upload to your email. Okay, and finally, remember the weakest link theory. The strength of concrete is controlled by the weakest link. Okay, here shows some of our local aggregate, which is pretty porous. And we know the strength of porous aggregate will not be very high. Okay, so keep that in mind. And that's it for today's lecture.